Hello, sir. Hello. Okay, so welcome to the live session 2 of week 5 of the course Digital Electronic Circuits. So I'm Anan Singhal, a PhD student from IIT Jodhpur, and I'll be assisting you in solving week 5 tutorial problems, and this will help you in solving the problems of this year assignment. So we'll start with the week 5. So till now we have covered the basic uh, of digital circuits, they like the Boolean algebra, minimization, mux, demux, and combination circuits and all. So this week we'll cover the all the basic topics of number system and octal and hexadecimal numbers, the convergence, the complements. There are few codes also such as binary, gray, XS3 code. So we'll cover these topics in this week's uh, tutorial lecture. So in the last lecture, some of the students were asking the query about two questions of the multiplexer assignment, which was posted this year as assignment 4. So first of all, I'll be explaining these two questions which was asked by a few of the students. So, and then I'll cover the topics of the binary system. So, one of the students asked this question that it was not clear, so I'll try to cover it. Yeah. So, this question says that the following circuit diagram the propagation delay of a multiplexer, NOR gate, and the inverter are. So it is given that for the mux, the propagation delay is nothing but 1 nanosecond. Okay. And for NOR gate, it is 1.5 nanoseconds. For inverter, which is basically a NOT gate, it is nothing but zero point 0.5 nanoseconds. So if PQRST are applied at the same time, so we need to calculate the maximum possible propagation delay, it is saying. So now there can be two conditions for this problem. One is S0 is on and one is S0 is not on, because there is an inverter here, as you can see. So if I supply T as 0, so then S0, then this node will be on, and uh, as we know that when T0, so this node will be 1 and this node will be on. So the circuit will work something like this, and then this, and we'll get the output. And for the, if I say for the opposite thing, and if I take some different color, if T equals to 1, then this node will be 0. So now the circuit, since this is 1, so S0, this 1 will work, then from this mux, it will go towards this NOT gate, since now the S0 is 0, and the ultimate output we will receive like this. So if I talk about this purple one, so what will happen here is, let me change it, yeah. So for the purple one, what will happen is the propagation delay for the complete circuit will be, if I take T as 0, so there will be a propagation delay for NOR gate, then there will be a propagation delay for this mux 1, then there will be no propagation delay, and there will be a propagation delay of this mux 2. So if I calculate, it is given that NOR is 1.5, and then mux is 1 plus 1, so it will be 3.5 nanoseconds. And if I try to calculate the propagation delay for t equals to 1, then it will cover, so it will cover the propagation delay of the NOT gate plus mux 1. Then we have a propagation delay of this NOR gate, since it is coming in between. Then we have a propagation delay of this mux, and this is how we will receive the final output. So if I can try to calculate, so NOT gate is giving it zero point 0.5, then mux is 1, then again NOR gate is giving as 1.5, and then mux is again 1. So if I try to calculate this total propagation delay, so it will be 3.5 and then 4 nanoseconds. So the question says that what will be the maximum possible propagation delay in this question. So it will be nothing but 4 nanoseconds. So the correct answer to this problem was 4 nanoseconds. So this was a query asked by a student in the last lecture. So I tried to cover it up. Uh, this was from assignment 4, not 5. I hope you understood it. If there is any query, I can repeat it again if you want to. Let me proceed to the next question. So if you have any query, you can type in the chat box. So this was another question asked by the student from assignment 4 only, that uh, what are the possible maximum expression of the output of the given circuit. So it was quite easy actually. There is only one output which will got denied by this demux, and from this node we can clearly say that the maximum, whatever maximum we will receive, will only have a single maximum, since there is only one output which is giving a NOT gate. So in the shortcut also we can say that the answer will be this term only. But to elaborate, I can write that we know that in the given question f is nothing but I naught plus this is I2, and then this is 3 4 5, this is I5. So this is f, and all are the floating terminals. So floating terminals are always high in case of a demux. So what will happen is, if I try to make the truth table of it, it will be nothing but ABC, and then D have a possible two values. So for 0 0 0, D will have a 0 1. For again 0 1 0, D will have a 0 1. Then similarly for, oh sorry, this will be 0 0 1, and then 0 1 0, D will have again 0 1. My bad. This is this, and 0, 1. So we know that for I2 it is given that a not will not be considered. So if I take 0, 1, 0, 1, if D is 1, then only the term will be 0. Else all the cases will be 1, because it is a demax. So output F everywhere will be 1 except this term. So if I try to write the min terms out of it, so every term will come except this term, which is 0, 1, 0, 1. So 0, 1, 0, 1 is nothing but 5. So if I try to calculate the output of it, it will be nothing but uh, max term 5. So the correct answer to this question was option D. So these were the two questions that were asked by students uh, in the previous lecture. So I tried to cover it up in this lecture, and now we'll start with the binary algebra and uh, my bad, not binary algebra. This number systems, yeah. So number systems, we can have few basic questions. Yeah. First of all, this is a basic question which will make you familiarize with the binary system. So this is a log-based question. So it says log to the base 2, 512 is x. Then we need to find x. So for this, we need to know few of the properties of log. So if log a to the base uh, a, so if the variable inside and the base is same, then log is always 1. This is one of the property of log. Then log, let's say it is base log b to the base a, and b has a power c. So it is nothing but c log a and b. So these are few properties of log that we will require to solve this question. So it is given in the question. It is log 2 to the power log 512 to the base 2. So we know that 512 is nothing but 2 to the power 9. So now I can write, from using this property, I can write this as 9 log 2 and then 2. I hope you understood this. This power has been multiplied with the term now, and we know that from the property that if the base and the inside term is same, then it will always be 1. So the correct answer to this question will be 9 only, which is option D. I hope it is clear. This is quite a simple problem. Okay, so let's move to some more problems. So this is one of the problems from Radix. So I'll try to solve it. So it says 125 to the base r is 203 to the base 5. So we need to calculate its radix 5. Radius is or base. These both are the same thing. So we need to have a like basic understanding of how to convert uh, one of the basis to some other basis. So for that there is nothing but a basic formula that whatever is the base, we need to start from the zeroth power of it, and then we should multiply it by, for the ones digit we need to multiply it by 5 to the power 1. Then for the next digit we need to multiply it by 5 to the power 2, and it will go on till whatever the number of digits will be. And one of the main things that we need to check is the inside term should not be greater than this value of the radix, since the base 5 can only contain terms up to value of 4. So let's suppose if it was written here 205 to the base 5, so this is wrong, it is not possible. Even like 206 to the base 5, it is not possible. The maximum term that can be possible here is 444 to the base 5. We cannot write the terms above n minus 1, and n is the base that I'm talking about. So if I try to convert this RHS, which is 203 to the base 5, it will be nothing but, if I try to write it, something like 2 into 5 to the power 2 plus 0 into 5 to the power 1 plus 3 into 5 to the power 0. This will be nothing but 3 plus 0 plus, and then this will be 50. This will be 53, and similarly for R we will write the same thing. So it will be nothing but 1 into R square plus 2 into R to the power 1 and 5 into r to the power 0. So if I try to solve it, it will be nothing but r square plus 2r plus 5. So in the question it is given that 1 is equals to 2. So if I write it, it will be nothing but r square plus 2r plus 5. It will be equal to 53. So it will be nothing but r square plus 2r minus 48 to the equals to 0. So if I try to factorize it, it will be nothing but 2, 4, 6, so 4, 8 and 6, yeah. So it will be nothing but plus 8r minus 6r minus 48 equals to 0. So it will be nothing but r plus 8 r minus 6 is equals to 0. So for the final value, if I try to write, so there will be two values. So I'll change the color maybe. So r will come as minus 8 and 6. So we know that this radix cannot be negative. This number system only applied for the positive value of the integers. So the correct answer to this question will be 6 only, which is option D. So let me go above also. I'm not written it correctly, I guess. Yeah. So if I say the correct answer to this question was option B, and then for this it was D, and then this it was again D, and then it was D. Yeah. So now I'll make you familiarize with the binary, no, not the binary, but decimal to some other base system conversion. So as we saw in the above problem, it was also similar. So let's see here also. So it says that we need to okay, convert these to their decimal equivalent. So as we did in the above problem, we'll approach this problem exactly in a similar way. So it will be now it says something after decimal. So there is a convention that after decimal, let's suppose here it is 5. So we'll not start with the 0, we'll start with directly from minus 1. So let there will be some more terms. So it will be nothing but then minus 2, then there will be minus 3 and so on. So this is the convention for decimal digits. So if I try to solve this problem, so uh, it will be nothing but 1, 2, 3, 4. So it will be 4 into 5 to the power 3 plus 0 into 5 square, and then 2 into 5 to the power 1, and then 1 into 5 to the power 0. And if I write after decimal, it will be 2 into 5 to the power minus 1. And this will be to the base 10 now because we are converting to the decimal equivalent. So here we can write 125 4, that is nothing but 600 plus 10 plus 1, and then after that it will be 2 by 5, which is nothing but zero point 0.4. Yeah, so it will be 611.4 to the base 10. You can convert or check it by converting now the decimal to the 5-digit conversion. So it will become same. So the answer for this question is this. And there is one more question which is B65F to the base 16, and you need to calculate its decimal equivalent. So it is again similar, so I'll write it somewhere else maybe. Let me try to cover it here. So it says B65F. Yeah. So B65F to the base 16, and we need to convert it to the decimal equivalent. So for hexadecimal, we know that from 1 to 9, it is represented by the same decimal digits. And since it is 16, so all the numbers will be covered till 15. So after that, 10, 11, 12, 13, 14, 15. So they are represented by A, B, C, D, E, F. So in the question also there are a few representations like that. So it says that we need to convert it into the decimal equivalent. So it will be nothing but B. So from here we can check that B is 11. So I can write B, then 16, 0, 1, 2, 0, 1, 2, 3. Then it will be 16 cube. Then it will be 6 into 16 square. Then it will be 5 into 16 to the power 1. And then f is nothing but 15. Here we can check. Into 16 to the power 0, which is nothing but 1. So 16 cube is nothing but, I don't remember, I guess 4096 into 11 plus then 16 square is 256 into 6, and then 16 5 is nothing but 80, and this is 15. So if I multiply 4096 by 11, it will be 45056, plus then if I multiply this 256 with 6, it will be 1536. Then this is 95. So if I try to add up all these terms, this is nothing but 45056, and then I have a 95. So it will come as 46687, and this is to the base 10. So this number, if I try to convert it to its decimal equivalent, it will be nothing but this. I hope this is clear. This topic is quite easy, and we are covering quite a later week, so I hope it is already clear to you, these basic things. So this was a basic idea of how we can convert different bases to their decimal equivalent and vice versa. So these two questions are from Mux, and then I covered some of the basic mathematics questions where we can use this log property, and then there are a few again the basics of this radix questions, like how can we find out the radix if we have some different number system or the different representation of the base. Then I try to make you familiar with the how to convert some of the basic numbers from any base to their decimal equivalent, which is nothing but base 10. So we got to know that for this, I'll write it again. For this, the answer came out to be 611.4 to the base 10, and for this, it was nothing but 46687 to the base 10. You can check by calculating yourself. I have done the calculations manually, so you can also check doing simultaneously if you want. So yes, we shall proceed now. So these are again few questions of decimal numbers to their indicated values. So we need to calculate, these are the decimal numbers. Now we need to convert them to the octal, hexadecimal, and binary values. So yeah, so this is quite interesting. If there is a way to do that. So for octal, easier method is first convert the decimal number to its binary equivalent, and then make a pair of every three binary digits, and that will give you the final octal representation. So I'll try to solve it. I'll make it simpler for you. So let's not go into decimals. So let's suppose the question only says that this is some base 10 and we need to convert it to its octal equivalent. Octal is 8. So for this, what we'll do is we'll convert it to its binary equivalent first. So 7562. So how we can do that? It will be nothing but 7562 by 2. It will be uh, okay. 81 and the decimal is 0, then 3781. Then you have 1890 and the carry is 1, then 1890 by 2. It will be nothing but 945 and the carry will be 0, and then 945 by 2 is 472 and the carry will be 1, and 472 by 2. This is nothing but 2 and 3 and 6. Carry will be 0. 236 by 2, it will be nothing but 1.8. Again the carry will be 0. Then let me like this. Then 118 by 2, it is nothing but 5. So then 59. Again the carry will be 0. 59 to the base 2 is nothing but 28. Again the carry will be 0. 29 actually. 29 by 2 is 14. Carry will be 1. 14 by 2 is 7. Carry will be 0. Then 7 by 2 is 3. Carry will be 1. Then 3 by 2 is 1. And the carry will be 1. So if I write it in the reverse order, so I will start from here. It will be 1101. Let me write it 1101 and then here. So from here I am going now here. It will be 000. And from here I am going here again 01, and then from here I am going here. It is 01. Okay, let's come to the next page. Yeah, and then from 01 it is last at 0. So this is the binary equivalent, sorry, decimal equivalent of the given. This is a decimal number, so I've calculated the binary equivalent of it in the next digit. So I need to change it to the octal equivalent. So I have given you the shortcut that you can take three digits, pair of three digits, and whatever the number comes, it is the octal equivalent of it. So 110 is nothing but 6, then 100 is 4, then this 001 is 1, and then 010 is 2. So it will be nothing but 6412 to the base 8. If I convert this 7562 only to the base 10 to base 8, so it will be nothing but 6. Let me check what was that. 6412. So again, we can perform the same uh, for these also. You can take these as a homework problem. So I'll try to cover this to binary problem because it will take a 10 less amount of time. So it says that 175 to the base 10, and we need to convert it to the binary. So we know that 175. So it will be nothing but 128. This is again a shortcut. You need to find out the maximum 2 to the power equivalent of this one. So it is not 256. It is between 256 and 128. So I've written the 128, and then it will be 128 plus not 64 plus 0 into 64. Again 32. Yes, it is 32. So it has already covered like 160. So not 16, then 8. 168 is there, then 4. 172 is there. Yeah, so it is nothing but 128, which is 2 to the power 9. Oh, not 9. 0, 1, 2, 3, 4, 5, 6, 7. Then this is 0 into 2 to the power 6, then 1 into 2 to the power 5, then 0 into 2 to the power 4, then 1 into 2 to the power 3, and similarly with uh, sorry, 1 into 2 to the power 2, plus 1 into 2 to the power 1 and then plus 1 into 2 to the power 0. So if I try to write it, it is 2 to the power 7, which is 1 0 1 0 1 1 1 1. So this is to the base 2. So for 175 we can write the binary equivalent as this. I hope it is clear. This is quite easy. So this is the answer to 175 to the base 10. This is nothing but this to the base 2. And I have also made you clear that how can you convert binary to octal. So it is quite easy. You just need to take some pairs. First you need to calculate this number. I guess there will be one more, one here at the last. Yeah, this will be 1 by 2. Then I guess I missed one here. So I guess this is not the answer. So this will be 101, 010, 000, 100, and 001. Yeah. It will be 1, 5, 0, 2, and then 5 to the base 8. You can check simultaneously by multiplying it by 8. Consecutive 8 to the power like 5. Then 5 into 8 to the power 4. And similarly, I guess this is 4, 3, 2, 1, 0. Yeah. You will get the decimal equivalent, so you can even check it by doing that. I hope it is clear. So I have one more question similar to this, which will further clear your doubts if you are having any. So let's take this. Now this question says, let me erase it first. This question says that the hexagonal representation of 7214 to the base 8 and 3645 to the base 8 hexadecimal. So what we need to convert, we have something to the base 8 and we need to convert it to the base 60. So it also has a certain method of doing that. So I'll try to teach you that how to convert it. So again, the easier method I'll try to cover. So easier method or the shortcut to convert octal to its hexadecimal equivalent. So for this, what you can do is whatever octal digit you have been given, you first convert it to its binary equivalent, and then you can easily convert it to its hexadecimal equivalent. So this is the shortcut that I'll be explaining using a problem which I have taken. So let's do one case first. So first case says that 7214 to the base 8. What is the hexadecimal equivalent of this? So if I try to cover here, so if I try to make the binary equivalent of it, so we just need to write the binary terms for the terms associated to it. So it will be for 7 it is we know 111, and for 2 we know it is 010. For 1 it is nothing but 001, and for 4 it is 100. So the octal to binary, so it is quite easy. This is the octal to binary conversion. We just need to write whatever decimal equivalent we have of the following terms given inside the octal in a pair of 3. So here you can see this is a pair of 3. So let me undo it. Yeah, so this is 7, this is 2, this is 1, and then this is 4. So now after converting it to its binary equivalent, take a pair of 4 4 from the from the LSB, which is the least significant bit. So this is 4, then this is 4, and then this is 4. So whatever this 4 4 pairs, just write its hexadecimal equivalent and you will directly get the answer. So this is the shortcut associated to this problem. So for the first case, it is nothing but 1100. So I'll try to write for A, B, C, D. 9 we know that it is 9, but for after that it is A, B, C, D, E, F. So A is 10, B is 11, C is 12, D is 13, E is 14, and then F is 15. So 110 is nothing but 12, so which is C. So I have C here, and then it is 1000, which is 8 directly, and then it is 1110. So 1110 is nothing but 14, and 14 is divided by E. So for the first part, which is 7214 to the base 8, we have calculated the hexadecimal equivalent quite easily just by converting the octal to its binary equivalent and then to its hexadecimal equivalent. So let's see. So we have eliminated A and C. So similarly, now we'll approach the same using this method for this 3645. So let's start doing that also. 3645 to the base 8. So I'll try to solve it. So 3 is nothing but 0, 1, 1. Then 6 is nothing but 1, 1, 0. Then 4 is nothing but 1, 0, 0. And then 5 is 1, 0, 1 to the base 2. So again I'll write. So this is nothing but 3. Then this 6. This is 4. Then this is 5. So this is a pair of 3. Now I'll make a pair of 4 from MSB only. So this is one pair. Then this is one pair. And then the rest is this is one pair. So now I'll try to write the equivalent. So this is 0, 1, 0, 1, which is 5. Then this is 1, 0, 1, 0, which is 8 plus 2, which is 10. 10 is denoted by A. And then this is 0, 1, 1, 1, which is 7. So for the second part, that is 3, 6, 4, 5, the hexadecimal equivalent is nothing but 7A5, which is given by option D. So we have eliminated D also. So the correct answer to this question is option D. I'll write it. Yeah. Yeah. This does not have any options. So this was for the basic understanding of how to convert different bases or different numbers to their some different bases. So we have also calculated that how can we convert octal to hexadecimal, or similarly we can convert hexadecimal to octal also by converting it first to their binary equivalent and then doing it for the octal part. So I hope it is clear. It is quite easier to solve these type of problem. So I guess we can proceed. Okay, so this is a basic question of nines complement. So complement is nothing but complement is like complement. We know that complement to positive is negative, negative to is positive. So there are few denotions in the binary number systems, not the binary number system, but in the number systems, there is an arithmetic associated to it. So we can calculate n's complement just by there is a method to. I'll change the color. Yeah, so there's a method to change any number to their nines or the n's complement. So it is nothing but whatever the number is, we'll take the maximum number that we can relate to that. So here we know that it is 1, 2, 3, 4, 5, 6. So it is a six-digit number. So the maximum nines complement is 9999999. We'll just subtract this number from that. So if I directly subtract it, it will be 9 9. Then it will be Okay, wait. Then it will be 2, then it will be 5, it will be 3, and then it will be 4. So 435,299. So you can see that if we have a n's complement, so we just write whatever the n is and whatever the number is, and just multiply n by that number, and we can directly get the digits. So it is like that. So if I try to convert this now, so we just need to subtract every digit by the number given. So 9's complement is given, so 9 minus 0 will be 9, then 9 minus 1 will be 8, then 9 minus 2 will be 7, then 9 minus 3 will be 6, then 9 minus 9 will be 0, and then 9 minus 8 will be 1. So this is the 9's complement of 0, 1, 2, 3, 9, 8. So let's suppose if in the question instead of 9's complement, you take a question, yeah, calculate maybe 6 complement of 1, 2, 0, 5, and then 3. So yeah, first of all, you need to be clear that for the 6 complement, this digit cannot be greater than 6. Then it will the subtraction will be something negative, so it is not possible to calculate the 6 complement of that number. So I can write it directly that 6 minus 1 is 5, then 6 minus 2 is 4, then 6 minus 0 is 6, then 6 minus 5 is 1, then 6 minus 6 is 3. So this is the 6 complement of this 12053. So this is the basic understanding that how we can find the uh, complements of the direct decimal base number. So we'll cover the complement which are ones complement and twos complement, which are quite important in the later session. I mean later in this session only. So for now, this is a basic understanding of converting these nines complement or n's complement from a decimal base number. So I hope it is clear. So I'll proceed now. So again, this is a radix question. So I have already told you the way to calculate this. So I'll calculate it maybe in a minute. Okay, so it says that if 125 to the base r is 55 to the base 7, then what will be the value of the radix? So it's quite easy. So let's do it again. So for the LHS, we know that it is 125 to the base r. So it will be nothing but 1 into r square into r to the power 1, then 5 into r to the power 0. So if I try to solve it further, it will be r square plus 2r plus 5. Then for the RHS part, it is 55 to the base 7. So it is 5 into 7 to the power 1, and then 5 into 7 to the power 0. So it is 35 plus 5, which is 40. I hope it is clear. So according to question 1 is equals to 2. So it will be r square plus 2r uh, minus 35 equals to 0. So it is nothing but r square plus 7r minus 5r minus 35 equals to 0. So if I try to factorize it, it will be r plus 7 r minus 5 equals to 0. So we are getting two values of r, which is minus 7 and plus 5. We know that this system cannot be in negative, so this is not possible. So the correct answer uh, this question will be only the positive one, which is 5. So the correct answer to this problem is option C, which is 5. So this is a similar question that we covered earlier in this session only. That how can you convert these? Not convert. How can you find a different number system or the different base of a particular number? So we have find out that 125 when we take as a base 5, it will be nothing but same to 55 when we take as base 7. So just like that, maybe you can also take a look and we can wait for maybe 5 minutes now. If you have any doubt, you can ask. Let me try to summarize also. So we started this session with two of the previous assignment problem which were asked by a certain student. Then if we try to cover the number system, so the first question that I discussed about was a mathematics based question which tells about some properties of log. So we studied two major properties of log that we used to solve the question. It was quite basic. Then there was a question where we need to find us some different base in the number system so that these two numbers can be equivalent. So 125 will be equivalent to 203 to the base 5 in some other radix system. So we try to calculate by simple equations and by equating them, and we can find out that if we take the base 6, so then 125 to the base 6 will be equal to the 203 that is given in the question to the base 5. So now I made you understand that how can we convert basic digits into their decimal equivalent. So it is quite easy that whatever the number is, we just need to calculate it, multiply them by their simultaneous nth power. So for the zero digit, we need to multiply it by 5 to the power 0, then 5 to the power 1, and then so on. And after the decimal, it starts with 5 to the power minus 1. So this was some of the basic understanding of the conversion of any base to their decimal equivalent. Decimal equivalent is base 10. So now from the decimal equivalent, we try to find out that how can we convert the number to their octal and hexadecimal. So just to have some clarity, I just missed the decimal digits here and just directly found out what is the decimal equivalent of this 7562, which was some large number, and we found out that this is the decimal equivalent. So the method to find out the octal equivalent from the decimal is we first need to convert it to its binary equivalent and then take a pair of three. So this is what I wrote here. So we first converted the number to its decimal equivalent, and in a pair of three we just calculated that this is the number. And for binary, we know that this is the method that we divided by 2 until we reach to a final 0. So I did it and reached. So for 175 also I calculated. I also presented one more method that you need to just check that if it is coming under what maximum power of 2. So 2 to the power 7 is nothing but 128 and 2 to the power 8 is 256. So this number is between, so we'll take the lower one. Similarly, now 128, so the left part is less than 64, so we'll not take 64, and then 32, so and so on. So this is one of the good methods from where we can find out that directly. So the answer to this question was nothing but 1 0, then 1, then 0, then 1 1 1 1 to the base 2. So this was 175 to the base 10. Yeah. Then I try to make you familiarize with how can we convert any octal representation to its hexadecimal or vice versa. We can also convert hexadecimal to its octal equivalent also. So this was another question that we covered, which was quite easy. So how can we do it? We can first convert the octal number to its binary equivalent, which is making a pair of 3. And to convert that to its hexadecimal equivalent, we need to make a pair of 4. So here I've done the same. So this is 4 4 4, and then directly write the number whatever is the decimal equivalent. So here I have written that for 12 it was C. So I've calculated, and the correct answer to this question was option D. Then we try to find out that there can be nines complement or n's complement of a number. So how can we find out those numbers? So and then again there was some radix question which I tried to cover. So this was till now. So now there are few not easier, some complicated problems that we'll try to solve now. We'll start in a minute. Okay, so here the question says that we need to convert this 125, sorry, 121 to the base 10 to its binary equivalent, such that the error between the actual and the decimal value is in the order is should be kept inside the order of 10 to the power minus 3, which is nothing but 0.001 or 1 milli. So if I try to calculate 121 in the binary system, so it will be nothing but 64, then 32, then 64 and 32 are 66, and then 96, and this is 16. It is 112, 112 plus 8, and then 0 plus no 4 required, no 2 required, and then 1. So this is the shortcut to calculate. I have already told you in the previous problem, so it will be nothing but 1 1 1 1 0 0 1. Okay, so we have eliminated this option D. So 121 is nothing but this. And now if I try to calculate this point 0.6, it says, so point 0.6 will be nothing but uh, point 0.6 is, we know that we have to start with this 2 to the power minus 1, which is nothing but zero point 0.5. So it will be 1 into zero point 0.5, then zero point 0.6 we need to have, so we cannot go for 0.25. Then even 0.125 will exceed that number, so to the minus 3. Yeah, then 0.125, the half of that will not exceed. So 2 to the power minus 4, it will be nothing but, I guess, 0.0625. And then this was again zero point 0.5. If I try to add them up, it will be nothing but 0.5625. Okay, I guess still, if I try to calculate the error now, so this is zero point 0.6, this is 0.5265. So zero point 0.6 minus 0.5625. So it will be 5, 7, and 3, then 0. So the error is 37 milli still. So error is 37.5 into 10 to the minus 3. So it is not inside the given range. So this cannot be the answer to this question. So we need to take one more, which is 2 to the minus 5. And then that is 0.03. 1. Okay, wait. 0.125 divided 2, it is 0.0625. So it is 0.03125. So if I add these numbers 0.03125, so it will be nothing but 5 and then 7 and then 3 and then 9 and then 5. So now if I try to calculate the error, it is zero point 0.6 and now it is 0.53795. So it is 5, then 2, then 6, then 0, then 0. So now it is in the order of 6 into 10 given minus 3 milli. So now it is in a single digit order. So that is why the correct answer to this question is option A. It was quite easier, just the calculation part was quite complex. So the correct answer to this question is option A. Let me write it in some different color. So A is the answer to this question. Okay, so we'll start in a minute the next problem. You can note down this. I hope this is clear. So let's proceed now. Okay, so this is again a question which is related to the concept that we have already discussed. So it says that 6 AED point D26 D2C only. Sorry, D2C with a base 16 and we need to calculate its decimal equivalent. Not decimal, it's binary. So it is again easy. So for hexadecimal, we know that we need to make a pair of 4. So 6 is nothing but 0, 1, 1, 0. A is, okay, I'll write it again for your convenience. It is 10, 10, 11, 12, 13, 14, 15. So A is 10, 10 is 1. Okay, my bad. It is 1, 0, 1, 0. Then E is 14, which is 1, 1, 1, 0. Yeah. Then D is nothing but 13. So 13 is nothing but 8, 8 plus 4 plus 1. Yeah. So this is the binary equivalent of the number given in the right side. So I guess all the options no. So 110. Okay, so this option is eliminated and 110, 110, 110, 010, then 1110, and then 110, and then 1101. This is also eliminated. Now for D, we know that D is nothing but 13. So 13 is 1101. Then 2 is nothing but 0010. And then C is nothing but C is nothing but 1100. So we know that uh, after decimal digit, these last two digits are not significant. So the correct answer to this question will be, and before this we can discard this zero, and after this we can discard these zeros. So 1 1 0 1 0 1 1 1 0 1 0 1 0 0 1 1. So this will be the binary equivalent. So this is not okay. So this is also not the answer. So the correct answer to this question is option A. I hope it is clear. These are the calculation based questions. You can note down, or it is quite easy. So these are just the binary conversions. It requires more calculation than the conceptual knowledge. Again, this was a calculation based, complete calculation based question. It requires some mathematical calculation, and again, this is just playing with numbers. Okay, so we can proceed now. Yeah. So this is another question where again, so now the question says that we have been given a certain radix and we need to calculate what can be these numbers P and Q. P and Q are question mark in this question. So if I try to write, okay, I'll write it in the easier way. So it is nothing but 0, 1, 2, 3, 4. So it is nothing but 5 into 8 to the power 4 plus P into 8 to the power 3 plus 3 into 8 square, and then it is nothing but 6 into 8 to the power 1, and then last it is 4 into 8 to the power 0. And similarly, if I try to write the RHS, so this was the LHS. So if I try to write RHS, which is nothing but 5 into 16 to the power, so this is nothing but 0, 1, 2, 3. And then A. A is nothing but 10. I hope it is clear. A is 10. So A is 16 to the power 2, and then F is nothing but 15 into 16 to the power 2. Oh, not 2, it is 1. And then Q into 16 to the power 0. So it is quite easier. I guess you can see if I try, take two common from every term, so it is nothing but 8 into 2 Q square. So we know that 8 cube is nothing but 8 into 8 into 8, and 16 square is 16 into 16, which is 8 into 8 into 8, 64 and 256. 16 square is also 256. So we can directly see that this 8 cube is nothing but this 16 square. And then this term also is the same. 16 cube is nothing but 8 to the power 4. So it is nothing but 5 is same here. Then P and 10 can be compared. And then F is 15, and then 8 square and 16 to the power 1. So 8 square, if I try to write, it is nothing but 8 into 8. So it will be nothing but, I guess, 12 into 8, 16 to the power 1, which are same, and then 4 into 8 to the power 0. So these equations are comparable. So we can directly compare, and we can write this. If I try to take 2 common out of them, so then 2b will come out as 8. And then this q will directly come out as 4. So if I try to compare this equation, then p will be 5 and then q will be 4. This was again a quite mathematical problem, not some concepts are required in this problem. So the correct answer to this problem is option A. So this is just calculation based questions. Uh, you can note down this question. We can do the same in the next question in maybe 2 minutes. So the next question is again similar to this problem. So it says then 1 into a to the power 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. A to the power 4, then 1 into a to the power 3, and then p into a to the power 2, and then 1 into a to the power 1, and then this q into a to the power 0. If I try to write the LHS in the same manner, so it is nothing but 1 into 16, 0 into 3, then 2 into 16 square. So these two are same. We can directly see, and then C is nothing but ABC. So 10, 11, 12. So 12 into 16, and then plus 9 into 16 to the power 0. So now the same thing, if I try to compare it, and there we can check it quite clearly. So now we need to calculate the value of P and Q in this problem, which are quite easy. So maybe you can compare equation 1 and 2. So we will get P as 3 and Q as 7. You can check this. This is just mathematical problem. Maybe we can proceed to next problem. So these two problems are exactly similar. So that is why I'm not solving much in this. I'm just telling you the way how we can calculate it. So let's move towards the next question. So the next question says that a decimal number 23.60 is converted to its binary as this. So we need to calculate the value of m and n. So this is quite easy again. Okay, so let's see. So 23.60. We can directly. So this is a decimal, so we can calculate its binary, which is quite easy. 23 is nothing but we know 16 plus not 8, then 16 plus 4 plus 2 plus 1. Yeah, it is nothing but 10110. I hope it is clear now. So from the options we can directly say that the value of m is 1. So we have eliminated these two options. Now we need to calculate the value of n. So zero point 0.60. So zero point 0.60 is greater than zero point 0.5. So again it will start from 1 into 2 to the power minus 1. So here we can see that it will start with a 1, so n will be 1. So we have eliminated these option also. This and this. So option correct answer to this question will be option A, but we'll calculate that as a predefined number. So this is 1 into 2 to the power minus 1, and then 0 into 2 to the power minus 2, because 1.125 is greater than this zero point 0.6. And then again, if we want to write maybe another 0 as 2 to the power minus 3, which is nothing but let me see, 0.125 half is 0.0265, so it is getting greater than 0.03125, and then again it this by 2. So we can clearly see the first term will be 1, so this will give 0.15 plus something something something, uh, and it will reach to something 22.60. So the moment we got to know that the first one will be n, because this point is given in the question is greater than zero point 0.5, so this is the same method we have applied to the decimal side of it. So the answer to this question will be m is also 1, that we have calculated from 23 decimals equivalent, and n is also 1. The correct answer to this question is option A. I hope it is clear. It was quite easy. We'll proceed to the next question in a minute. So it is again calculation based. Maybe you can try that too. So it says that 11000.111 to the base 2 upon 100.0011 to the base 2 into 1000.11 to the base 2. So we need to calculate it in decimal. So we can proceed with, this is zero point 0.5 plus 0.25, which is 0.75. Okay, so zero point 0.5 plus 0.25 plus 0.125, which is 57.875. So this is nothing but 2 to the 0. Okay, let me invert. 2 to the power 0, 1, 2, 3, 4. So 8 plus 16, this is 24.875. And when we divide it by 0, 1, 2, 3, so 1, 2, 3. So this is 12.125. This is 0.125 and then 0.0625. So 578. This is 0.1875 to the base 10. And then if I try to write this is nothing but 0, 1, 2, 3, 4, 5. So 32 plus 16 is 48.75. So we can directly use the calculator to solve this problem. So I'm using the calculator, so it is 24.875. Then it is divided by this 12.875. Okay, so this is the division part, and then the whole part is in the multiplication with this. So I've written it wrong. Maybe, yeah. So this whole part is the complete multiplication. So into this 1100000.11 to the base 2, which was 48.75. So I'll write it into 48.75 to the base 10. So into 48.75. So you can calculate, so it is coming out as something 97 to the base 10. The correct answer to this question is option D. I hope it is clear. It is quite easy. Just some mathematical calculations required. Okay, so we can proceed now. Okay, so this is at the subtraction of 3375 minus. So we need to subtract the number also and tell that what will be the base 8 and base 16. So for this we need to have some. We have already learned that for the conversion of an octal number to a hexadecimal number, what we need to have its binary equivalent. So subtraction of binary equivalents, what we need is 2's complement. So first we'll read the concept of 2's complement, then we can proceed for this question. So maybe I can go for some other question which can, yeah. So I'll tell you the concept of one's complements and two's complement first. So this question can cover that. So here for the given binary digits, we need to calculate the ones and two's complement. So one's complement is nothing but the complement of all the digits. So let's suppose this is A, B, C. So for A it is 1 1 0 1 0 1 0 1. So the ones complement of the same will be 0 0 1 0 1 0 1 0. Just flipping all the digits will give its ones complement. So if I go with B now, so that ones complement will be 0 1 0 1 0 1 0 1. And for C it is again 0 1 1 0 1 0 1 0. And to calculate the two's complement, we just need to add 1 in the ones complement. So 1, if I try it, so this is the two's complement of the number. Similarly, I'll write it here. So 1 plus 1 is 0. And this will be same. Then if I write here, it will be 1 1 0 1 0 1 1 0. So two's complement helps us in solving these kind of problems. So maybe I can tell you some methods to subtract the numbers using two's complement first. Then we'll reach to that problem which we were discussing above. So given we have given two numbers which are, one is x 1 0 1 0 1 0 0, and second is y which is 1 0 0 0 0, okay, 1 1. So the a part says that we need to get x minus y, so it is nothing but x plus 2's complements of y. So we'll first calculate the 2's complements of y, which is nothing but y is 1 0 0 0 1 1. I guess it is 4 times 0. Okay, one more 0 is there. So for calculating 2's complement, we will first calculate the 1's complement of y, which is 0 1 1 1 1 0 0, and then we'll add 1 to it. So the 2's complement will be 0 1 1 1 1 0 1. And ultimately, what we want is x minus y, right? So that is x plus this 2's complement. So I'm directly writing this. I'm directly writing this x as this 1 0 1 0 1 0 0, and then 2's complement of y was this 0 1 1 1 1 0 1. So if I add it, it will be nothing but 1 0 0, then 0, then 1, then 0, then 0, then 1. So there is a carry, so we can discard it. So the answer to this question will be, if there is a carry, we can directly discard it. So it will be 0 0 1 0 0 0 1 answer. So these are the signed bits. So the answer to this question is directly after discarding the bit, whatever comes is the answer. And if we are not getting a carry, then we need to calculate the 2's complement again. So that will be the final answer, which will be a case for y minus x. So I'll do that maybe in some other page. So y minus x, I'll write x and y again, 1 0 1 0 1 0 0. And y is 1. Yes, this was it. Yes. Now we need to calculate y minus x. So what we need is y plus 2's complements of x. So 2's complement is x. So x is this. So 1's complement will be 0 1 0 1 0 1 1. And then 2's complement will need to add 1. 2's of x will be 0 0 1 1 0 0 1. So now y minus x will be y plus 2's complement of x. So I'm writing y as this, and then plus this 0 1 0 1 1 0 0. It is nothing but 1 1 1 1 0 1 1. So there is no carry. So for final answer, we need to get 2's complement again. It is nothing but 2's complement of this number will be 0 0 1 0 0 0 0 plus 1. It will be nothing but 1 0 0 0 then 1 0 0. The correct answer is again it is coming as same, which is y minus x answer. You can check from both the cases the answer is coming out to be same. It's just that we have discarded carry, so this was minus 17 and the last answer is plus 17. I hope it is clear now so that we can proceed to the question that was given in the assignment. Yeah. So here you can see that we need to minus, first of all, we need to convert them to their binary equivalent. So 3 is nothing but 101, then again 101, then, oh, not 101, sorry. 3 is 011, then 011, then 5 is 101, and then 7 is 111. This is binary equivalent, and then minus 001, then 7 is 111, then again 111, and then 010. So we need to get the 2's complement of this, then add this. So I'm writing the 1's complement directly. So this is plus 1's is 11000000. This is 11000000, and then 2 is 101. So I've added this number as 101. So this is a 1 complement and I'm adding 1. So this will be the 2's complement. So the final answer will be that. Plus 1 is nothing but 0, 1, then all will be same. I'm writing it here 1100, 7 zeros are there. And then 110. I'm adding this. This is 1, then 0, then it will be 1, then it will be again 0, then it will be 1, 1, 1, 1, 0, 1. 1 and 1 will be again 0, and then 1, 0. We can discard the carry, so directly the answer to this problem will be this 0 0 or whatever is this. So now we can make a pair of 3 to get the octal equivalent of it. So it is nothing but, let me use some different pens. So this is this, then this, then this, and then this. So this will be 5, then 110 will be 6, then 011 will be 3, and then this will be 1. So it is nothing but 1365 to the base 8. So we have discarded these two options. So options will be from 1365. So we can directly convert this 1365 to its hexadecimal. So we have already know the shortcut. So this one is 001, then this 3 is 011, and then 110, and then 101. So we can take a pair of 4 now. So this is 4, then this is 4. Yeah. If I try to write it, it is nothing but 2. Then all ones are there, then it is F, then it is 5 to the base 16. So we have eliminated this. The correct answer to this problem is option B. So this is one of the problems that required a knowledge of hexadecimal to octal or octal to hexadecimal conversion in both one's complements and two's complements so that we can finally find out the answer using that. I hope it is clear. So this was quite good problem. Maybe we can proceed now. Okay, so this is again a similar problem. So it says this A is this thing and B is this. Then so these are 8-bit signed. So signed means that first digit always corresponds to the sign. So the first digit, if I try to calculate, it is nothing but this is the sign. So A will be nothing but 1 1 1 1 1 1 0 1. Then B is already positive. So it is 0 0 0 0 1 0 1 0. So this is nothing but plus 10. And then this is nothing but if you this is a negative number, so we need to calculate the two's complement of it. So it will be 0 0 0 0. How many ones are there? 6. And then 1 0 plus 1. So it will be 1 1 0 0 0 0 0. Since there is no carry, it is minus 3. So A is nothing but minus 3 and B is nothing but plus 10. So A cross B will be minus 30. And for minus 30, we need to calculate, since it is a negative number, we need to calculate the two's complement of it again. So it will be 30 is denoted by 16 plus 8 plus 4 plus 4 plus 2 plus 0. Yeah. So how many people have 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. So this one is for the negative. If I try to calculate the two's complement, so it will be 1, 1, 0, 0, 0, 0. There will be 4 zeros and then 1 plus 1. So it will be 1, 0, 0, 0, 0, 1, 1 and then 1. The correct answer to this problem will be 1, 1, 1, 0, 0, 0, 1, 0, which is option B. I hope it is same. Yeah. So this is how we can directly calculate this. This is again one of the concepts that you need to learn. Maybe we can proceed now. So now this is a full adder question. So a 1-bit full adder, we know that a full adder is, we can make a full adder using two half adders also, but a full adder is nothing but it adds and gives the case carry output. So it says a full adder, which is a 1-bit full adder. It takes 90 seconds to produce some, 30 seconds, nanoseconds to produce carry, and we have a 8-bit parallel adder. So the minimum propagation delay it is asking. Okay, so this is a shortcut problem also. So as soon as you see that the propagation delay of sum is greater than that of carry, you can directly use the formula that the minimum propagation delay will be nothing but the sum propagation delay plus whatever the number of parallel bit address they were using. So it was a 8-bit parallel adder, so it will be n minus 1. So I'm writing the general formula, then carry generation delay. So in the question it is given that it is 90 nanoseconds and it is a 8-bit, so it will be 8 minus 1, and then the carry generation delay was 30 nanoseconds. So it will be 90 plus 7 into 30, which is nothing but 90 plus 210, which is 300 nanoseconds. So the correct answer to this question is option D. So this will be the minimum propagation delay that will be required. I hope it is clear. Maybe we can proceed to the next problem. Yeah. Okay, so it is again. So we know that for a half adder, sum is given by A XOR B and carry is given by nothing but A into B. So the question is asking that what will be the values of S2 and C2 in the question. So it is given that A and B are the input of this adder. So S1 will be nothing but A XOR B. S2 will be nothing but A into B. Now they are getting ANDed. So S1 into C1 will be nothing but A XOR B and with AB. So A XOR B is nothing but AB bar plus A bar B into AB. So if we multiply this, this will be B bar into, so we have already wrote it, X bar is 0, A into A is A. So it will be 0 and then plus 0. So the input to this, both the hardware adders will be 0. So sum will be 0 XOR 0. So S2 will be this, which is nothing but 0. And then C2 will be again 0 into 0, which will be 0. So the value of S2 and C2 respectively are 0 and 0. The correct answer to this problem is option D. So I hope I try to cover the basics of the all the circuits that we can. And then again I have tried to clear the concept of ones complements and twos complement using some example. Then there were some binary to decimal conversion and octal to hexadecimal conversion in the problems. This was one more problem of some different approach. So I hope it is clear now. You can go through them again once, and if there is any doubt, you can always reach out to me in the next session. So yeah, you can see them, and then we can wrap up this session now, I guess. Thank you for attending the session. It was great. We shall meet in the next session now, which is I guess scheduled on Wednesday. Not this Wednesday, maybe on the next Wednesday. NPTEL will let you know. So thank you for the attending the session. Yeah, thank you all.